Hello, my name is Pablo Ortega and I'm studying Robotics and Digital Systems Engineering at Tec de Monterrey. This video is a brief overview of the research I conducted on evaluation of motion prediction in ground airport operations as part of the 2023 Robotics Institute Summer Scholars Program. I would like to begin stating the broader case for motion prediction. When navigating in a multi-agent and dynamic environment, notion of future movement of surrounding actors is indispensable for safety, as it allows for the proactive and preemptive identification and avoidance of dangerous scenarios. The self-driving domain has led the charge in motion forecasting, as this type of task proves indispensable for coordination of autonomous vehicles. On the other hand, aviation is another field with a great need for safety-critical systems that has seldom explored motion forecasting. A prime example where such models could be extremely useful is the detection of runway incursions, situations where pilot or air traffic control error causes an aircraft to stray into an active runway zone. The work seeks to advance the development of a motion forecasting framework for aviation by tackling the matter of context. Specifically, we aim to introduce a dataset of airport ground operations and provide two forms of context representation. We then integrate context encoders to a novel framework under development by Carnegie Mellon University and assess the impact of different map representations on the learned trajectories. For the proposed evaluation, we will be employing a transformer-based model. The model adopts an agent-centric encoding scheme, meaning that given a scene within agents, we transform each trajectory to the viewpoint of the actor by shifting the sequence such that the starting point is the origin, and rotating about the agent's heading. For feature extraction, a late fusion approach is taken, meaning there is a separate type of encoder for each modality of information, and the features are concatenated at the end. Note that since this is a transformer-based architecture, positional encoding is also used. The full feature vectors are fed into a GPT-2 style causal transformer, which performs multi-head temporal attention. Each decoder in the stack is made up by layer normalization, followed by multi-head attention, and then a feed-forward neural network, followed by a final layer of layer normalization. To capture the multimodality of future trajectories, outputs are modeled as distributions using a Gaussian mixture model. Regarding the data use, trajectories were collected using the Federal Aviation Administration System-Wide Information Management. In particular, we use the Swim Terminal Data Distribution System. We collect data for 200 days and processes such that information is grouped into 30-second-long sequences. Given that Swim uses a publisher-based scheme rather than polling, interpretation is necessary. For context, we are provided HD maps in the OpenStreetMap format. We process these to generate a raster and graph representation. For raster, it represents the polygons formed by the map elements as shapes on an image. We color code each section based on the semantic type. For the graph, we further process the provided information. We first must remove all nodes and edges that do not correspond to the center line of a movement area. We also must imbue the pertinent semantic information to each node. For this, we encode the categorical values using one-hot encoding. We then pad the center line via the nodes along each runway. We also take advantage of this to connect every taxiway termination to the nearest runway, ensuring all movement zones are fully connected. We only keep the highest degree subgraph in our context graph. We also subsample nodes in the graph by consolidating redundant points between endpoints. Finally, we model the input in a vectorized manner. The attributes of each edge make up an array, and the graph is the collection of said arrays. To verify the processing of the graph was correct, we project trajectories onto it. We propose two different context encoders, one for each representation. For raster images, we use two convolutional layers followed by a linear layer to project linear features. For vectorized representation, we use a multi-layer perceptor. We present results obtained by training the model on 35% of the data. We compare the average displacement error, which is the average L2 distance along the trajectory, and the final displacement error, which is the L2 distance at the last time tip of the forecast horizon. We can see that even though the metrics are within the same range, the raster-based approach seems to have a slight advantage. Looking into qualitative results, we plot scenes with the best and worst metric scoring and compare the produced trajectories. We first notice that the two models have the highest and lowest ADE in the same scenes, hinting that the models hold similar information. Furthermore, even though the generated trajectories differ, this does not happen in a consistent way. Sometimes the model trained on a graph-based context shows less multimodality than the raster-based context, while other times it's the other way around. This means that we cannot make a definitive conclusion of whether these changes are because of the context representation used or just other factors that influence in that specific scene. In conclusion, both representations yield similar performance, hinting that they hold equivalent information in their context. Raster performs slightly better than the vectorized, but the vectorized version is cheaper and easier to be processed and run. Furthermore, leveraging more suitable methods for spatial aggregation, like graph neural networks, could help the vectorized representation yield improved performance. For further work, we would like to explore the use of graph neural networks to perform this more advanced spatial aggregation. We would also like to use the graph to constrain predictions to movement areas. Having the graph structure can also allow us to simplify existing trajectories in using the graph space and explore methods like viewpoint invariance, what will allow us to make a more robust model, as well as cut back on pre-processing times, because the per agent transformation would be able to be foregone. Finally, I would like to thank the viewer for paying attention, but especially the RI community, Rachel Bursin, Dr. John Dolan, Dr. Gino, my mentor Ingrid Navarro, and all the other friends I made along the way. This has been an amazing experience, and I'm very grateful that I was able to take part.